Hello everyone, welcome to the workshop. Please welcome Travis.
Howdy everybody. So I hope from the pre-start explanation you're all installing the software now. What we're going to do today is we're going to first install free CAD software for reverse engineering mask ROMs out of microchips. We're then going to take photographs of a small region of the CPU of a Nintendo Game Boy, and we're going to mark out all of the ones and the zeros of the mask ROM in that Game Boy. And then when we have all of them, we're going to convert them back to the bytes that you would logically find in the memory. They're spread around physically, so a single byte will cover the entire width of the ROM. It's not written all together like in English or in Serbian. And then by doing that conversion, we'll then have a copy of the program that the Game Boy runs when it first turns on. If you've ever used a Game Boy, this is the program that slides down a little Nintendo logo and plays a little chime and compares the Nintendo logo in the ROM to a matching logo in the game cartridge. This is the way that the copy protection works on the Nintendo Game Boy. In order for your cartridge to boot, it has to have a Nintendo logo. And if you have not licensed that logo from Nintendo, they will sue you until the ends of the earth, and your great-grandchildren will die penniless. And then the game can begin. It's a very short ROM. It's about 256 bytes. It sits at address 0 in memory. And as a little copy protection measure, it disables itself as it jumps into the game cartridge so that the game cartridge is never allowed to read the ROM out. So you're not able to read this out by software. You instead need to read it out physically, and that's what we'll be doing today. For the new arrivals, I have two URLs on the screen. If you are running Mac or Linux, you're going to go to the first URL, which will redirect you to GitHub. On Linux, you will follow the build instructions. On Mac, you will download the latest pre-built executable. And we have pre-built executables for both ARM and for x86. On Windows, I screwed up the pre-built executable in the most recent release. So you'll instead use this second URL with the .zip file, and that should work for you. As you get this installed and running, we need a signal or something. I don't know, wave at me, or we're gonna spend the next 7 minutes on this, and at the end of the hour, then we're gonna get started with actually reverse engineering the ROM. If you get blocked for any reason, please flag either me or Alex down, and we're more than happy to help unblock you and keep this moving. So after you get this running, on the README file of the GitHub repository, there's a link to GB-ROM tutorial, and that contains the picture that you need to download to open in mask ROM tool. You can either do this by cloning the Git repository, or you can just download the BMP file. It's BMP because lossful compression can confuse the image recognition. And basically, this one photograph contains the computer program. You can open up in mask ROM tool to begin annotating it. And it has some instructions for how to add rows and columns to it. The way that this tool works is that we're going to draw a line through every row and a line through every column, and wherever they intersect, that's where the software will insert a bit. And for 256 bits, it's going to give us, for 256 bytes, it's going to give us about 2,000 bits. And then we're going to export that as ASCII art, and we're going to use a command line tool called gato-rom to search around and try scrambling this in all sorts of different ways until it figures out the way that makes sense as a Z80 program, meaning that it begins by setting the stack pointer. All right, so we're going to begin. I'd like you to play along on your own machine. So you should have the same file open as I do, and you should have the you should be looking at this same screen on your own machine. Now the picture that we have here is rather magnified. So we can see the bits. The bits are in very, very wide lines. And at the very beginning, our crosshair, which is a bit faint on the screen, but you should see it on your own. Our crosshair is at a perfect like 0 and 180 degree angle. As we begin drawing lines, our crosshair is going to tilt. And we're tilting the crosshair because even though our photograph is not perfectly arranged for right angles, it is consistently arranged inside of itself, meaning that our rows and our columns will be 90 degrees apart from each other. Now, because this image is so wide, it's hard to see both the left side and the right side at the same time. And there's a trick for that, which is that we can go to our view menu, and down here it says second view. And what this will do is it pops open a second window of the exact same image, and our crosshair appears on both, which means that I can have I can click on either my left view or my right view, and as I start dropping row lines, I can do that across the entire width of my project, even though my screen isn't wide enough to hold that width at a resolution where I could accurately hit the bits. Now I'm going to zoom in on this view, and these little dots here, the dark ones, those are ones. And wherever the dark splotch is missing, that's a 0. This is called a VIA-ROM. And that dark splotch is a vertical connection between layers inside of the microchip. Because we're looking at like multiple layers on top of each other. And in those multiple layers, we're only looking at the top. That's why some of the features in the background become blurry, because we have silicon in the way and the focal depth of my microscope is not very deep. We're going to start by drawing a line through just a few bits, and then later on we're going to delete our work, and then we're going to do many more bits. So I want you to use a single view and to show maybe eight columns in width, and you don't need to show many rows at this point. We're going to do the really long bits later. Mask-ROM tool is based on a concept of like a set position compared to the mouse position. So whenever you click, you are setting a position that you will work against through other commands. So we're going to click once to the far left of our 8-bit row. And I'm just doing this with my touchpad, just one little click. And there's no indication from the software or response from that position. I then move my mouse to the right side of that row, and I hit the R key. And the R key draws a black line through all of those bits from where I had first clicked my mouse until the new location. I then move my mouse down until the new row is highlighted, and this particular image is almost at right angles, so you don't notice it, but your crosshair has switched. Could someone close the door? So as I move my mouse down, I'm now on the right side, and the angle looks right, but I do not hit the R key, because if I hit the R key again, it's going to draw a row from the same set position. And I want a row of the same angle, but with a different destination position. And I do this by holding the Shift key and pressing R. For convenience, you can also use the spacebar for this. So I move down a little, and I hit the spacebar again, and again, and again, and again, and I've now marked out 6 short rows of my leftmost column. If my image is very well aligned, I will never make rows this short, except for like demonstration purposes or to figure out my colors. If my image is poorly aligned, then I will frequently do this in order to take care of breaking, in that sometimes the pictures don't perfectly line up, and that fracture between them can make the angles change a little bit. So if I have very long rows, I might only mark them halfway. And the reason why I'm marking it from the right side is I generally want the origin point, the side that I do not control, to be on the outer edge. That way, if I'm a little bit too close to the line or a little bit far away, I'm not going to overlap any more columns. Now that I've got these rows in place, I'm going to draw my first column. So first I go above the upper left bit, just above it, and I click once to set my origin position. And as you do this on your own machine, you'll notice that the vertical crosshair does not quite line up with the row of bits. It's drifting a little bit, and the bottom side is going further to the left, and it will very quickly go off of the column. This isn't a problem, because as soon as I drop my first column, the crosshair will correct itself and readjust. So I click once at the top, and then I move my mouse down to the bottom, and I hit the C key to drop a column. And not only does the column appear, but also my crosshair adjusts, and also my first 6 bits have appeared. I then move beneath the second column, and I hit Shift C. The third column, Shift C, my fourth column, Shift C, my fifth column, Shift C, my sixth column, Shift C, seventh and eighth. So now I've got all of these bits arranged, and they're all blue for the moment because the software doesn't yet know the color difference between a 1 and a 0. Yes? Right, excellent question. So sometimes when you draw these rows and these columns, either you're going to realize early that you placed it in the wrong position, or you're going to realize later on in the project that it's in the wrong position. So let's pick this row here. This is my third row. You see it there in blue. Let's suppose that this is the wrong position. Well, if I select it, I can select it by dragging my mouse, and the crosshairs will duplicate, and I'll see like a little square around it. And I'm trying to select only that one object. So this position on the screen is good in that I'm selecting just the row line. This is bad because I'm also selecting a bit and a column line. And there are reasons I might want to do that later, but not for deleting one row. So as I select my one row, I then release my mouse, and my crosshair goes back to normal. Now that it's selected, I can either move it or I can delete it. If I hit the S key, it will move around. It jumps to wherever my mouse is, and I'm able to move it onto the bits or off of the bits, onto the bits or off of the bits. If I want to delete it, I hit the D key, and it immediately disappears and it's gone. Sometimes when you're correcting errors, it's easy to delete the extra row, delete the damaged rows, and then go back to fill them in later, rather than to try and correct their position immediately. So then I still need a row there, so I move my mouse back and I hit the space bar and a new row appears. Does anyone else have any questions before we move on to setting the colors? Yes? Exactly. Okay, so when I said that you want Shift C or Shift R to repeat the same angle, if you forget to do that, you can make your crosshair like absolutely bonkers. It'll move off by many, many degrees. In order to fix that, all you do is draw another row or another column in like correct alignment with your project, and it will immediately fix your crosshairs. You do need to set a start position again in order to draw the fresh row, and that should correct it for you. Anyone else have questions before we get to colors? All right. So as you can see here, we've got all of these bits marked, but they're all blue. They're all zeros. And that's because the software does not yet know the color difference between a 1 and a 0. In order to do that, because we've marked not all of the bits, we've marked a lot of them so far. So we go to the Edit menu and choose Choose Bit Threshold. It's the very first item in your Edit menu. And this pops up a histogram. And the histogram is cool because it shows you how often particular values of each color channel appear. If we had a black image, then everything would be 0, and we would only have like 3 red, green, and blue lines on the far left. And if everything were 1, then we'd have the opposite. Sorry, if everything were white, then we'd have the opposite. Everything would be on the far right. Now, you'll see what we're looking for here is a bimodal distribution. A bimodal distribution is where many of the bits of a 0 have a color in one region, and all of the 1s have a color in another region, and we want a firm gap between them in which we never see that color value at all. And you can see this in both red and in green. Red has a central peak near the middle and like a really bright peak out to the right. And if we move the line between them, we see that it gets many of our colors correct. We can do the same thing in green, and green will get many of them correct. And as we slide this, we're basically just changing the threshold. Later on, after we've marked all of these bits, we're going to get a couple of them in the wrong positions, and we'll get a couple of colors that fit in that middle region, and we'll sort of look for those in order to identify errors. But this is all that we need to do in order to identify the, the first couple of dozen bits of our project. All right, is everyone up to this point, or do you have any questions before we move on to marking larger regions of the chip, like whole rows and whole columns? All right, good to go. Okay, so earlier we deleted one line, and we did that by selecting a line like that, and then hitting the D key in order to delete it. You can also use Shift D in order to delete groups of objects. So if I select 2 lines and I do Shift D, both of them disappear. I can do the same thing in order to delete all of my lines and all of my bits. Now, I'm not quite back to where I started because the software already knows the threshold between a 1 and a 0, and I already have my crosshairs in the appropriate positions. All right, is everyone up to this stage where you have deleted your prior work and you're ready to begin drawing longer lines? Awesome. Okay, so I'm now going to make use of seeing the same project in different positions. So I'm going to take my 2 windows and I'm going to drag them so that they are on separate sides of my screen. So I've got a left view and I've got a right view. On my left view, I'm going to move to the upper left of the ROM, where I can see the very first few rows and the very first few columns. On my right view, I'm going to go to the far opposite side of the chip, all the way over. So now I'm seeing the first few rows, but I'm seeing the very last columns. And you'll note that these are in different positions, but my crosshair from the left also appears on the right, and my crosshair on the right also appears on the left. And this is cool because I can drag my mouse, I can move my mouse over to just to the left of the first bit, just like I did before. You'll see that my crosshair is not quite in the right position on the right side, and that's because I've drawn short rows, so I've not had the distance to get my angle perfect. All of the positions maintained in this software are in floating point rather than integer, so that we can do things like very long lines with maintained angles and exactly the same drift. So after I lay my first line of the entire width of the chip, it should correct all of the drift, and my crosshair then ought to fully cover the width. So I click once to the left of the very first bit in the first row, and then I move my mouse to the right-hand side, and I go just a little bit to the right of the rightmost bit on that side, and I hit the R key. And not only does it draw a line across the entire width, but it also corrects my drift. So my crosshair now accurately fits all of the bits from one side to the other. If I don't like the fit of this, if I think that it drifted a little bit, I can always delete that and then draw another row in order to correct it. And it's remembering my old start location, so I do not need to click on the left side again. I only need to hit the button on the right side. After I've drawn my first one, I can move my line to the second one. And now that my crosshair is accurate, I'm able to see where it's going to get dropped. So you can see on the left side that the white line covers all of the left bits. And you can see on the right side that it covers all of the right bits. At that point, I hit a space bar or a Shift R, and I drop another row. Now the rows here appear in pairs. So I've got 2 rows, and then I've got a gap between them. Always remember to recognize the gaps that have no bits in them and to skip over them. In addition to those gaps, you're going to see vias elsewhere. Like on the left side, I have some vias that connect the rows to each other. Those are not bits. Those are just other vertical wires within the chip. So now on your own screen, begin marking all of the rows of the project. You won't see bits yet because you've not marked the columns, but we're going to mark the columns after we do the rows, and through that we're then going to get the whole chip. And if you finish marking the rows before I do, feel free to begin dropping columns using the C and Shift-C commands until bits have appeared for the whole project. And at that point, we're then going to do design rule checks, error correction, and then we're going to get bytes out of the ROM. I've got 2 questions, so you first. There is no undo shortcut. I feel bad. It's like IDA Pro or something. I will fix that soon. Yes? Oh, excellent question. So he's asking, when we draw that line, and our angle is, it's never going to be absolutely perfect. There are 2 reasons that it might be imperfect. The first is that the image itself is made up of 40 separate photographs taken under a microscope that have been combined into a collage or a panorama. Those images do not fit perfectly together, especially if the photographer is rushing. So sometimes you will find that over the course of the image, there's a little drift, and the middle of the image might go up and then back down by the end. In that case, you need to make shorter rows. On this particular image, all of the lines are rather straight, and you should not have a problem making a row from the far left to the far right, so long as the leftmost bit is crossed roughly in the middle, and the rightmost bit is also crossed in the middle. And if you find that there is drift by the time you get to the bottom, I'm actually going to spot check that by jumping to the bottom. You can fix that by just doing one more manual line. But as you can see here in my image, manually placing one at the very bottom does fit for this particular image. When we get to other project files, you'll find that they do not line up so well, and they require manual corrections. Yeah, like you would mark all of the bits on the left and then all of the bits on the right. And you can do this because the row and the column lines that you're marking right now are only there to discover the positions of the bits. They are not necessarily the same as the rows and the columns in our output file. So if you have a troublesome row and you need to draw it 1 bit at a time, you can do like 100 really short rows, and the software does not care about that, and it will perfectly line them up. Yes. Yes. So wherever a row crosses a line, that becomes a bit. The intersections are detected in order to create the bits, and the bit positions are the only things that are used for sampling. And there's an algorithm that looks at all the bit positions and then figures out where the real rows and columns are, but it does not respect the lines for that. Yes? Oh, yes. Excellent question. So he's saying that if you press Shift-C or Shift-R, you will repeat a row or a column. And he's asking if it's possible to repeat a group of them, like 4 rows or something. That feature is not yet supported. It is on the roadmap. By doing only the rows and the columns, you basically need to mark the square root of the number of bits in your project. And I've found that aligning more complex objects like a grid becomes troublesome over large sizes. So I've not yet found it necessary in projects beneath 100,000 bits. Cool. All right, so please mark your rows and your columns, and then we can continue on. And remember, as you drop them, to watch on the left side in order to ensure that all of the bits are crossed. A common mistake is to drift your line out a little bit and to not cross the leftmost bit as you're setting the right side. Yeah, so when you zoom out, you'll see that it tiles your image and shows you multiple copies of it. Basically, I was lazy a year ago, and inside of the source code, the image that you're working on is set as the background image, which creates a negligible performance benefit to collision detection, but also has that side effect of the duplication. And remember that if you have a problem with your particular project file, you can flag either me down or Alex down. We can take a look and tell you which keys to hit to fix whatever problem you have. And when you get to marking columns, the columns are in groups of 8. Remember not to mark the divider between the columns, because that does not contain bits. So here in my left pane, you can see that there are bits on the left and the right side of that center line, but that center line does not contain bits itself. No, we'll be using GatoROM for this tutorial. ZORROM is a predecessor to GatoROM. ZORROM invented a lot of the techniques that we're going to be using for the decoding, but MaskROM tool includes its own ROM bit decoder now, through which we can do the same solving and the same solution. I'm going to double check that that got pushed up to the README. Yeah. So after you mark all of the bits, if you want to jump ahead, skip the decoding with ZORROM section and jump ahead to the decoding with GatoROM section. Unless you want to learn all the tools under the sun, in which case ZORROM did come first, and it did make ROM decoding a lot less painful than it used to be. All right. As you mark up these bits, is anyone stuck, or does anyone have like a line in the wrong place? a question, or or you're stuck? Okay, Alex will swing by and help you with that. And remember that if you're, remember that the crosshair is showing you the angle of your previous row. So if you drew a bad one and now you're drawing a good one, the crosshair will be off. The quick way to work around that is you can hit R to drop a row line and then D to immediately erase it. And then your crosshair will fit with what you're about to draw. So now we're going to get to error correction. Are any of you still marking up bits within your Game Boy ROM? Great. We got one on the left. Do you mind if I continue? All right, cool. All right. So here I have my color threshold, and I've marked all of the bits. Your histogram here will look slightly different because your bit positions are slightly different than mine. The current sampler is the default one. We also have a wide and a tall. What the wide one will do is it will take a few pixels width and it will find the darkest color within that width. This is handy for diffusion ROMs where the bit is not so much like a dark circle as a line on the border. And this is because diffusion ROMs are very low in the chip and the diffusion layer is rather clear, so you're not looking for the color of the layer itself, you're looking for the border lines around it. We're going to leave that on default because we don't need to change it, but we are going to play around with our green slide bar. And if we get it too far to the left, everything becomes a 0, and if we get it too far to the right, everything becomes a 1. The correct placement is just in the middle of all of these two green mountains in the histogram, but we're not going to look at it there. We're going to move it just a little bit to the leg of the left mountain and pretend that we got it wrong. We then go back to our main window and we hit the V key. And the V key runs design rule checks. And if you do this, it's going to then tell you that you have ambiguous bits. These are bits that are so close to the threshold that the software does not believe that they are correct. It's not saying that they are wrong, it's saying that they might be wrong. And if we click on the first one, for me that's 8.3, and I zoom in. Now, you'll note that the blue box actually blocks a lot of the bit, and it's in my way, and I want to see the bit because I'm trying to know by my own eyes whether this is correct or incorrect. In order to show and hide all of the bits, and also the status boxes around them, like the yellow box that tells me that this is a design rule check warning, I just hit the tab key. And as I hit the tab key, all of my bits disappear. And I usually hit it a few times to make them blink. And you'll note that this blue one is over a dark bit, like this ought to be red, but it's over like the shiniest part of the bit, and that's what makes it close to the threshold. Now I've artificially introduced this because I chose a bad threshold in order to cause these problems. But pretend for a moment that I had placed my line in the wrong position, or that there was a little scab of dirt in my image. In that case, I move my mouse over the bit, and I hit Shift and F. And that makes it red, and it puts a little green box around it. A green box indicates that the value of a bit is forced. I'm forcing it as a human being because I am a person, and this is a machine, and the machine will do what I tell it and not the other way around. I then hit the V key to run the design rule checks again, and that little yellow border will disappear and the rule violation with it. I used to have 8 rule violations, now I'm down to 7. On your own image, if you keep your threshold in the appropriate location, and then you hit the V key, either a rule violation box will pop up, or the status line at the very bottom of the window will tell you that it has found 0 design rule check violations. Who here has a violation? Like, who sees one in the, all right, you got one? You got one? Who does not see one? Who got everything right on the first try? All right, congratulations to you folks. For the rest of you, please run it. Make sure that you see the rules go up. If you don't have any violations to fix, what you can do is you can cause one. I'm going to do this by dragging a line out of position. So I'm going to select a line, and I'm going to use the S key to move it to the very top. And I hit the V key, and now it's telling me that I have 6 rule violations. And it gives me the coordinates. Ambiguous bit 8,79, ambiguous bit 8,90. All of these bits are on row number 8. When you're on a very big project file, when you're looking at it like 100,000 bits, you're going to find that the errors group up. They will either group up because you misplaced a line, or they will group up because a particular spot of the image is misaligned. Sometimes it's handy to use the layers menu to take out the bits, but to leave the errors, and then you'll see like a whole chunk of yellow boxes all in the same position. So like in my case, a bit hard to see from the projector, but they're all in the same line. And when they're natural errors, you'll often find that like a whole region of the image is wrong. You also have the option in the DRC menu of choosing different tests. There's one that takes a very long time to run called duplicate bits, so I skip it. As development continues, more of these will be added. You'll also see that in the DRC menu, you can either evaluate the rules with a lowercase v, or you can evaluate all of the rules with an uppercase v. Evaluating all of them is handy because you can run the slow tests as well. So you can run the slow tests, walk off, get a coffee, come back, and only then find like the really rare stuff. Another really handy thing to do is to import the difference from another file. So I'm going to correct, well, no, I'm going to leave the errors in on mine. On yours, you should probably have it accurate. So go to File and then Export. And you're going to see in Export that you have a lot of different file formats that you can export to. So far, we've marked out the bits, but we've not found their positions. And finding the positions is either something that you can solve in a minute, as you can on this ROM, or something that you need to spend time on. For the MYK82 chip that I spoke about in yesterday's lecture, I basically moved to Bogota, Colombia for a week because I can't speak Spanish worth a shit and I had no friends there. And by the end of the week, I had made some local friends, I had drunk some excellent beer, had some absolutely fantastic ceviche, and I had solved the layout problem. And I solved the layout problem by bringing a lot of graph paper, and I'm sure the hotel maid thought that I was insane because she found just sheets of graph paper everywhere with little ones and zeros doodled in them. When you want to export to another tool, for example, if you want to, Chris Gerlinski has a tool for visualizing the bits that he calls Bit Viewer. For that, you use ASCII. And this just creates an ASCII art image of all of the bits. Every 1 becomes a 1, every 0 becomes a 0, you have a new line at the end of the line. This is sort of the standard format for working with this stuff. The CSV format is a comma-separated value. This becomes really easy to parse into any language, and you can open it directly in MATLAB or in Microsoft Excel. You can also do a JSON file of all of the bit positions and the attributes about them, like which ones are errors, which ones have drifted. That format can be really handy for doing things that operate on the image. Maybe if I wanted to make a giant poster and write my own software to do it. You can do a Python image. And for Mark IV and for ARM6, we can directly dump the ROM bytes. And more of those will appear very soon now that I've finished the library support for it. So go to Export, and choose ASCII. And it's going to give you like a file dialog. I just save it as bits.txt. And then because mine is, because I've got these design rule warnings, I'm going to fix them. Now I have 0 errors. And now I'm going to do something a little weird. So as you've saved your text file, please open it up in like Notepad or Emacs or Vim. If you do Nano, we won't make fun of you. And I just want you to change a couple of 1s to 0s in one spot. Like maybe in the upper left, just damage like 5 or 6 bits and save it. Okay? And when you do this on a real project, what you're going to do is you're basically going to do all of the work twice. We don't have time in the workshop, but what you would do is you would mark all of the bits in one set of photographs. You would save that, export it to a text file, and then you would do it all over again with a different set of photos from a different microchip after a different chemistry lab run. And you do this because the mistakes will be in different places. If you place a line wrong on one, you'll place it correctly on the other. If there's a speck of dust on one, there will not be a speck of dust on the other. The error rate on your project should be less than 1%, but that's still a lot of bits when you get to 100,000. So by doing this twice and then comparing them, we're able to highlight only the errors. So in my case, I have exported the bits from my damaged project. And now I go to the File menu after reopening the project. Or in your case, you can leave it open because you damaged the text file. I then go to File and Import, and I select ASCII diff. And what this does is it takes ASCII as input, and it compares it against the bits of my project. And if any of them disagree, it flags that as a warning. So I do ASCII diff, I select my bits.txt file. Okay, and now in my rules violation window here on the right, it's telling me that I have differing bit 878, 890. I can jump to the first one. So 878, it's this one here in blue. And this one is actually weird that that's correct. So this one's correct. So I select it, and I force it, and I want to force it back to be its own value. Oh, Shift F the first time will change the bit and force it. Do it again, and it changes it back. Oh, right. I've corrected my errors, so now all of these are correct positions. This is showing maybe what's wrong in the other file. So the other thing about doing this difference for error correction thing is that because your project does not have the errors that you inserted in the text file, you're in the good project and you're looking at the bad one. So when you do this on a real-world project, you will have 2 project files, 2 images, and you'll compare the 2 against each other, and you'll flip the bits that are wrong in your particular file until they match with, but only the ones that are wrong in your file. You then save it, you close it, export it, open up the other one, compare back against your first one, and fix the errors that are wrong on that side. And you just sort of bounce back and forth until they've all been reconciled. And at the end, you will have 2 large files with the same bits marked, but from different photographs at different times and different annotations. The last thing that we need to do is we need to take these bits and we need to get bytes out of them. So we go to export, we're going to do ASCII again, we're going to export it to bits.txt, and this is going to be the clean version. We're overwriting the errors that you introduced. Yes? There is. So like this one here has, we'll force this one. So say I force this to blue, it's now wrong, I realize I screwed up, and I don't want this automatic detection. You remember how earlier we selected just the line in order to delete the line? Or we could select multiple lines and then do Shift D in order to delete the group. So here I'm going to select a little bit of each of those boxes, and then I'm going to do Shift-D to delete them. And now my blue box is missing as well. I'm also missing the bit. But if I hit the M key, it comes right back. And the same happens for the V key or for anything else that recreates the bits out of nothing. All right, any other questions before we get to decoding to bytes? Great. So we go to export, we do the text file, save it as bits.txt, save my project and exit, and then I'm going to make this really big. All right, so we have all of these bits, and we know that the bits contain a computer program, and we know from a bit of history which microcontroller is within the Game Boy. It's not quite a Z80, but it's pretty close. If you go to the retro computing village down the hall, you're going to find the Voja Antonich's Galaxia. The Galaxia uses almost the same instruction set as the Game Boy. Minor changes, minor extra instructions, a couple of them missing. So as we have this text file, you can see that this is just clear text. This is just ones and zeros. We have a program called Gato-ROM, G-A-T-O-R-O-M. Again, I disappeared to Bogota in order to finish this, so Spanish was on the mind. If you run Gato-ROM --help, on Windows you will need to do this from cmd.exe within C:\maskrom tool. You'll find that it has decoders for a lot of different types of chips. It has decode ARM6, it has decode MSP430, decode TLCS47 font. All of these are classes that I've written in C++ to do particular types of ROM decoding. And a few of them are like calls down L, calls down R, calls left, calls right, squeeze LR. Those come from an earlier tool by John McMaster called Zor-ROM. Zor-ROM is written in Python. It operates on text strings. I needed a C++ library that was a bit more flexible than that, so I rewrote it, but while maintaining backward compatibility. So we can use Gato-ROM on our bits in order to do transformations. We can rotate it by like 90 degrees at a time, right? Because sometimes your photograph might be at a different angle than my photograph, or a photograph from one chip might be different from another chip. We can also flip them on either the x-axis or the y-axis in order to put the bits into a different position. We can also invert them, because sometimes the darker bit will be a 0 at one depth and it will be a 1 at another depth, and so you'll get it backward. And with all of these different settings, it can be very confusing to figure out what are the right ones for this particular chip. So we're going to use a solver instead. If you look on the tutorial page, you see that it has, Gato-ROM has this solve option. And we can either do solve bytes or solve string. Solve string is a little bit easier contextually, so that's what we're going to do here. On your command line, do Gato-ROM, and then your file name, which for me is just bits.txt, but you could have named it something fancier. And then the other things we add after it are --solve, which tells it that we're not going to give it all of the parameters. Instead, we're going to give it some things about the image and ask it to tell us which ones might be right. And then, as part of the solving, we're going to tell it that we want to do a string. And that string is going to be 31, FE, FF. A couple of important things to note. We're not saying that this string needs to be in the beginning, although it happens to be. We're just saying that the string needs to be anywhere within the ROM. A particularly good thing to look for would be the word copyright, because every now and then a ROM will include a copyright message. And if you can find the ASCII string, then you're home free. This particular value, 31 FE FF, is setting the stack pointer to the very top of RAM within the chip. When the chip comes out of reset, it does not automatically reset its registers. So on a Game Boy, the boot ROM is responsible in the startup sequence for setting the very first stack pointer in order to begin making calls. When we run this, the output is kind of cool. We get 3 different potential decodings, all of which have this string. They all have a grade 100 because they all have all 3 bytes in a row. And that output at the end where it's got like, decode calls down L, -I, -R0, -flip X, those are the parameters that we would apply to the executable in order to do that particular type of decoding. So of these 3, I can see from the hex, because I'm familiar with this image, that the middle one is the correct one. These hexadecimal bytes are the first few bytes of the output in order to allow the human operator to sort of quickly sort them. If this isn't enough, you can just dump them all out and then sort them later. You also have the option of, instead of like, instead of solving by a string, you can solve by another parameter. You can write your own solver solution. For example, a lot of MIPS and ARM code has like a function prologue that will be the same in many different functions, and you can add support for that. So now that I know that the middle one is the correct one, I'm going to use it and -o and foo.bin. Right, and I'm just copying the parameters off of what the solver solution gave me. I'm then going to hex dump that and pipe that into less, and these 256 bytes are the boot ROM of the Nintendo Game Boy that is responsible for the copy protection by identifying that the Nintendo logo in the cartridge matches the one in the ROM. It is also responsible for showing that logo on the screen. And this is how, if you made a game for the Game Boy that was not licensed by Nintendo, the boot ROM would force you to pretend that it was licensed by Nintendo in order to make it boot. And it's a nifty little Easter egg. If you have the wrong logo there, it will still show the logo, it just won't branch into the game. So. Within the tutorial, we've skipped today the earlier section on how to do this with XORROM. If you would like to do more development in mask ROM recovery, or you would like to extend GATA ROM to decode in different ways, it's very important to study XORROM, because that was the first tool that could do this automated solving in a way that works. You will also find, as you do real-world projects, that about half of chips are not solvable by these tools and require manual intervention. One trick that has been valuable has been to find an image ROM, like a font, to decode the font, because you can look at that and see when the pictures are wrong. And then after you have the font, going back to the code ROMs in order to figure out the software. It would also be valuable to have more of a visualization of where things are. One of the upcoming features to mask ROM tool is to show the hex editor output of GATA ROM directly, so that as you change the settings, you can see how the hexadecimal changes. And by highlighting over a hexadecimal byte, you can then visualize where the bits are within your image. And that's all that we have for the workshop today. So I hope that you enjoyed your first ROM recovery. If you have any further questions, feel free to ask now while I'm at the podium, or in 5 minutes we got to be out of this room, so feel free to meet me in the other room for a klubata or a coffee, and we can talk about it individually in person. So any questions before we leave the room? Yes? Or are you doing a shrug? Okay, well, pick one or the other.
If we have some additions, well, we can review the code, and if we have something that we want to suggest, and
oh yes,
maybe
so
some sort of things like ease of use, or like things that we would like to have included.
Yeah, so if you would like to suggest a new feature, at this point it's okay. But if this project becomes very popular, I'm going to start rejecting feature requests. So only for now, and only because you're in this workshop, and only because this project is rather new and used by few people, will I accept feature requests. File them on GitHub under the issue tracker, and please be very explicit about what the problem is, how you think it might be fixed, and how you would solve the problem. You do not need to include code. It does not need to be a pull request. But please be explicit about how a thing might work instead of just spitballing an idea. And the same goes if you find any mistakes or bugs. If you find a bug in the software and you're able to reproduce it, including the weird wonky Windows stretching error, please file a GitHub issue, say that there's a bug, explain how to reproduce it in as few steps as possible, and then I will reproduce it and I will fix it. Or I'll fail to reproduce it and blame a conspiracy and move on with my life. Cool. And we've already got a couple of bugs reported from in this workshop, and a few of those patches I've already pushed up. So yeah, thank you everybody.